Hello, welcome to ECS CDM 12 Media Computation. Today we're talking about filters. Hello, come on in, Ryan. Have a seat. So filters are interesting. You have probably used several of these in Photoshop or any of those touch-up services, apps, filters that you use when you take a photo. You may have even paid some photographer a big bunch of money for your school pictures to do touch-ups. It's usually like an add-on, that sort of thing. And most of the time what they do is they simply use filters. And we're going to talk about the math and the use cases of filters today. So by the end of the day, you could write your own. All right, so consider that you want to track a fly. And you simply have a camera that's taking bits of sensory data. A frame is getting all the RGB values from photons coming into sensors, putting that on one frame. And then it does it again and again and again. So you get these still photos, these still planes of pixels that represent the light image coming in, the light coming into the photo sensor at any chunk of time within its frame rate, right? So you get a still, a still, a still, a still, and what you want to do is track the position of a fly as it flies across the screen. And maybe you've all seen the Mark Rober video about like shooting squirrels with water cannons. Yeah, this is a similar problem. Now, what we want to do is like, the trick here is like you want to see how the pixels change. You want to see how this fly is moving on an otherwise static background. And there'll be some noise in the filter, like some leaves will move around when there's wind. Maybe light conditions will change as clouds pass. Perhaps there'll be dust streaming through windows, perhaps, or streaming through the light coming from windows. Perhaps there's a fish tank nearby and light is shining through it and there are caustics on a table. All of these things are a bit of noise, are features of the environment that aren't static, that are sort of compared to what we want to see, compared to our goal, aka tracking the fly, are visual clutter, things that will obfuscate what we're trying to do, make our problem a little harder. And maybe our goal is to reconstruct the fly's path. The problem is we can't rely on individual measurements because of the noise. So each frame is a little different. If you're simply looking at changes from frame to frame, it can be very hard to tell which changes are actually the fly or not. So the problem is we can't rely on these individual measurements. Each one of them are a little reliable. How do we proceed? Well, any ideas on what we do in this case? See if anybody's had some of this material before, has any intuition on how video processing works? Computer vision? Yeah?
I guess we could try and determine it based on color. So if we know what the color of the fly is, then we can have the thing look at just that type of color.
Yeah, exactly. Some like domain knob model of like what a fly looks like to a camera lens, right? Some bit of knowledge that you can maybe scan all the pixels and see if it matches that, right? A little pattern matching. Or pattern recognition algorithm. That's one good solution. Excellent. Anyone else? What about the path of the fly? This happens over time, right? The fly moves, changes locations. Now we have a sense of time here, right? We have a sequential set of images with the fly in it, just in different locations. Right? So how could we leverage that bit of information? Oh no, I'm asking for brain juice and it's early. No. Alarm Freak, come on in. Ooh, nice cut. All right, so the idea here is that most of the stuff is visual noise, but it's relatively in the same location, right? So now we can start comparing frame after frame after frame. Where are patterns of pixels that change pretty regularly in a spot, or where are ones that move. So the fly is moving, right? We want to capture a moving fly. So that's sort of one of our givens. So now we're actually looking for perhaps noise or changes from frame to frame that have some sort of motion to them, some sort of movement, a over time change in a direction or in a path. That in essence is what we're looking for, right? We're looking for this path over time or the change over pixels, locations of fly in video frame. So what we're looking for here is coherence between samples, where each video frame is a sample. And so looking at a few samples may give us a better picture of what's going on. And if noise in environments like regular, like photonic caustics coming through water, or a piece of paper flapping on a table, all these things over time, over enough image samples, will sort of become averaged out. Over the long term, like a minute of video, if you sort of average out the values of that area of video, it sort of becomes not noise. The noise variance gets captured in the average. But what wouldn't get captured in the average? A fly moving around, right? Because that's something that moves. It translates. It makes a bump in that smooth image of averages over time. And so that's what we can use to track. So instead of a single sample, we want to compute a weighted average of a couple samples and a couple after that and a couple after that to see where that movement is, where that coherence is broken. Right, so this type of reconstruction is called a filter. So here, if you look at the t values at the top, consider each one of those an image. Each one of those is an image at time. So ti is right now image. T minus 1, T minus 2 are 1 frame and 2 frames ago. T plus 1, plus 2, plus 3 are 1, 2, and 3 frames in the future. So you're looking at a sample, a pre-recorded video, and you're sliding through. You're looking at windows and a particular point in time in your video, and you're looking at frames before it and frames after it. And you're bringing all that information together to look for coherency. So this is sort of a filter. We're looking at a bunch of things around the one frame we care about to get information about it itself, about that coherency. So this is a weighted average, a window average. Right, so what we are here, this bottom frame here, this is all the information that we get about the image from looking at all the images around it, getting that weighted average. So this contains our information, our coherency information, perhaps where the fly is. Now, as you do another frame, you pop it over and look at the next sliding window. So now we sort of like get where the fly could be, where the coherency is broken in TI, and now we slide it over and do the same performance, the same analysis on TI plus 1. So now we have like this coherency information from frame to frame. And if we can find out where the coherency is broken from frame to frame, we have a good idea of where the fly is. And so if you do this slide this little 5-frame window over the entire video, you can reconstruct the path of the fly by simply looking at the area in the image where the coherence is broken. Right? Did I forget to? Okay, great. So what's interesting about this is this is a weighted average filter. And we'll talk about this a little more concretely as today goes on. But the weights that you get when you average all of these frames together, how you do that averaging, where you take that information from, defines the behavior of a filter. In this case, we're looking for coherency detection, where things change from frame to frame that are not the average. Right? And what's interesting about this is typically the rule of thumb we have here, unless you break it in very specific circumstances, is you want all those weights to add up to 1. So you take a fifth of t minus 1, a fifth of ti, a fifth of ti plus 1, a fifth of ti plus 2, a fifth of ti plus 3, and then sum those together. I mean, it's basically what an average is. So you want the weighted value of all these windows to add to 1. That basically makes it so the color balance stays correct. The intensity of the colors stay stable. Right? So the general picture here, popping back a moment, is we want input, we want to filter it, and that gives us something new, something transformed, some new information about the input as output. So we often use filters as tools. So here's an example. To run this example, you'll have to go to the Sketch menu option, go to Libraries, and load the video library for processing version 4. So you can go through and search by library by keyword, put in video, look for the video library for version 4 made by the Processing Foundation. All right, let's get this to code editor. Yeah, it should be background subtraction underscore Shiftman. Got to have the window title. There we go. So let's take a look at this and then we'll explain it a bit. Oh, okay, one moment. One moment. There we go. 2 applications cannot use my webcam at the same time. This is actually going to work now. There we are. So you see my face? It's actually picking up the screen behind me. But what we're doing now is what Zoom does. We're doing background noise cancellation. So it's looking at me as a feature. I am the thing breaking coherence, and so is my video at the top. Let me turn this a little bit so we don't have that. Okay, so now it's shifted. All the frame shifted, so everything behind me was seen as something coherent. Now, as I move, as I talk, as I motion with my hands, I am the variance against the background. So therefore, I'm adding my weight of pixels up the front. I am the fly. Everything that doesn't have a lot of variance, that isn't changing over time, is assumed to be background. And you can see as I move, it will then look at the pixel locations where I was and assume that's background as well. Right? So this is like, you can tell it's not as good as Zoom or Discord or Skype or whatever for background cancellation, but this is something in a few lines of code in processing that you can do for yourself, right? Filtering the foreground, aka the moving stuff, the stuff that breaks the coherence from the background. Let's look at the code. Processing output window. So basically what we're doing is we're using that coast image that we used a few times, and that's what we're replacing the non-changing tiles, the things that have coherence from frame to frame. We are replacing those with the image. And we're using the video stream and the pixels from it for things that break coherence. So we're setting background, setting a background image, we're creating an image. This is what we're going to be loading all of our information to. We're going to be deciding which pixels are background and which pixels are foreground. We're going to start the video command. So I guess one thing to note here is we're using or importing process.video.star. So this is a library that if you want to run this example, you'll have to go and load. This is a bunch of external code that processing will download for you, put onto your computer, that allows you to access your camera, to process video, etc. That stuff wasn't packaged with processing in its sort of like stock form. So this is a little mod we're downloading. A library, but a functionality. And basically what this boils down to is a bunch of class definitions, just like we talked about in the objects and arrays lecture. Yes?
Where do you go to download it?
You go to Sketch, and you can't see like the pop-up windows, but you down around here, it'll be import library. And then you go to Manage Libraries. There'll be a right arrow, context arrow. And then when you go into that, you'll have a bunch of libraries there. There'll be a filter box. You can type video in the filter box. And you'll want to look for Video Library for Processing 4. And the author for it will be Processing Foundation, the Processing Foundation. All right. So we got this, we're getting a capture object, a capture instance of capture class called video. We got our p images. We have a floating threshold, which will be a value we look at to determine whether the coherency is broken or not. And we're offsetting the image in the background a bit, just to center things a little bit. We're loading the image. We are displaying that image in the background. And now we're doing video capture. So we're capturing a frame from the video. And we're making a new blank image that we're going to start modifying and putting in the background. And then we're starting the video. So this is all in setup. All right, we're making a new capture object where we can capture frames from, I should say here. Sorry, I misspoke a little bit. And we're saying, hey, initialize the camera. Inside of Draw, we want to see if the video is available. If the video is available, we want to read a frame from it. So now our video, we can call load pixels to get the background image, the image on the window. We can call video.loadPixels to get the current frame of video that we just captured. And we're going to load images from the background picture, the coast image. So these are the three things we need, right? The video image, the background image, and the current state of the window. And so what we're doing is we're walking through every pixel in our window width, and we are going to do some math on it, right? So you can look at this example in the book as well. We're finding the pixel location, right? We're converting our XY coordinates to pixel array coordinates since it's a flat array like we talked about before. And then we're finding that location. So now we're getting that location in video. So we're starting at the top left corner, so index 1 of the video, and we're scrolling through the entire width of the video. And we're getting the color. So for the first time through this loop, we're getting the color of the top left coordinate of the video, incoming video, and we're getting the top left color of the background image, the coast. And now what we're doing is we are pulling out the color information for each one of those. And then we're looking at the distance. So we're using color functions as sort of like the distance from red 1 and red 2. So if one is 200 and the other's 100, the distance is 100 between the two. We're looking at the color difference on each color channel between the incoming video and the background. And so we're just getting a distance there. Like we used distance before to see whether your click was in a circle. So the difference between the middle of the circle and where you clicked, the distance between those, if it was greater than the radius, it was outside the circle. If it's less than the radius, it was inside the circle. We're using distance in a slightly different way here. So we want to know what the color difference is between the two. So what we're doing here is we're always putting the video, we're comparing the video to the background. So the background is our sort of our memory. It's what existed there before. It's the image, the T-1 image. And so we're looking at our camera value and seeing, hey, did the colors change? Is the distance between color in the background and color coming from the camera greater than a threshold? Is the distance greater than 30 in this case? And if it is, if it looks like it's changing from frame to frame, we want to put the foreground color in, or the color from the video, onto the screen at that location. Otherwise, we want to display a green color. Basically, we're using that as a green screenish metaphor to put in the coast background. How many of you are familiar with green screen? You seen this? Where they have a green background, like the weather, people use it, people on Twitch use it a lot. Okay, there's enough nodding that I won't explain it. But this is how green screening works too. This algorithm works great with green screen. All right, so now what we're trying to do is we want to copy the current state of the frame into the background. So this basically reinitializes our green screening process. So let's run it one more time now that we've seen the code a bit. There we go. It's loading the plugins. There we go. It's initialized my video. So right now, it's not really running. The current video is being put as the background. When I click now, it's going to start the green screen process. Click. And so if I stay very still, I can't stay still enough for this to work. I would disappear, right? If there is no movement, it will display only the background. As I move, that makes a color difference between the background pixels and the video pixels. So it is displaying the video pixels instead of the background. This makes sense? Do we demystify a little bit of one case of this video filter? This will be, we're going to use just static image filters for the rest of today. And then we're going to introduce video later in the class. But this is an example to help motivate this entire filter discussion. Questions? All right, back to the slides. Oh, where did my mouse go? Okay, two screen mouse problems. There we go. So that was background subtraction shiftment. Relatively small amount of code for the effect it does. I think it's kind of neat. All right. So you can get a lot of effects. You can keep reapplying filters. So basically it's just image data. You can do image data on top of image data. You can pull image data from many sources and bring them all and filter it together. You can apply like a bunch of filters on top of each other for cool effects. There's a lot you can do here. And this is called iterative filtering. Right, whether you filter more over time, you use the same filter multiple times, or you apply multiple filters. In this case, the filter we're doing is really applying a weighted average from the previous frame to the current frame, so TI and TI minus 1. And we're using those together as a little two data source, two image pipeline. So a lot of times you can apply a weighted average filter. So how many of you are familiar with Gaussian distributions? Right, sort of like a curve of likelihood, where 0 and 1 are the extremes are very low on the curve. And as you go from, I guess, 0 to 1, around 0.5, it peaks and then goes down when you go to 1. So what we're doing is like having a pretty normal, a nice distribution where the middle values occur more often than the values on the extremes. Right, so we'll be talking about this a bit. Like we'll be using Gaussian, a little bit of terms of Gaussian distribution today, and you'll kind of see what they look like inside of a filter matrix. And we'll also, when we talk about sound, we'll have more filter support. So I actually don't want to spend a lot of time on this in particular. We'll reiterate this material on these last two slides, iterative filtering and support, as the course goes on. All right, so let's work with images. So convolutions. How many of you heard of convolutions before? Excellent. Okay, so we have one person that's heard of convolutions, right? So basically, this is the idea. If you're looking at one pixel, maybe you want to modify it. Maybe you want that pixel's value to actually be related to the pixels next to it, or in an area around it. Right, so this bit of convolution, you can really, in the advanced definition here, for those of you who had calculus, a convolution can be thought of as an integral of the effects of one function and a second function, aka the filter plus the image. Right, so what we're doing is we are doing a bit of integration, but we won't go through the calculus math and the calculus portion of it in this class. We will look at the very practical version of it. So when we're looking at images, we have a common representation. We have pixels in a grid, right? And what can we do with pixels in a grid? Well, we can use filters. We can use filter shapes as grid of pixels and the entire image as a big pixel grid and have one affect the other. Basically put that filter on top of your image grid and look at the result that it has. So basically for this, we're doing sums instead of integrals. And this is where having the sum add up to 1 is very important for us. It makes more sense in the calculus, but the common understanding is that if the filter value is not 1, then you are somehow biasing the intensity or the brightness of the image. But it's easier to understand with an example. Let's stop free floating. So we'll motivate 1. So for every pixel, let's say we want to replace the pixel color with the average of its neighbors. And the mean of average can vary. In general, like a weighted average is important here, but we're just going to have a common average for now. So here is one. You can have a convolution that's done by replacing a pixel with the sum of its neighbors. Have you ever sharpened an image in Photoshop? This is what it's doing. This is exactly sharpen. You can modify the values a bit to get variance on sharpen, but this is the core sharpen algorithm. So notice we have this filter right here. So in our case, a filter is simply a small matrix, a small grid that is typically the same width as it is height. And they're usually odd width and height numbers, in this case 3. And note that we have -1, -1, -1, 9, -1, -1, -1, -1, right? So if you add up all of those values together, you have -8 plus 9 equals 1. This filter does equal to 1. It passes our little 1 test. And so this is how like the code would work on here. So if our filter is centered around pixel ij, we simply do a little bit we get the values of the pixel at that location, and we start applying this formula. So all the pixels except for ij, we subtract the value from our final convolution value. So what's doing is we want our color value of the pixel in the middle. It's defined as this. You take the negative of all the weights around it, and then you take the weight of itself times 9, and this actually sharpens the image. So right, you're biasing that image, that one pixel that you have, around its own color very strongly. And you're actually, instead of taking information from them, you're actually taking away the color values. You're taking away any color bias. You're actually de-averaging. You're taking out the color values from its neighbors. So you're making essentially separation from one pixel and its neighbors. You're making that color much more distinct from the colors around it. Sharpening. And so if you want to do this on an image, you want to do it for every pixel. One moment. Filter. I'm going to run an example right now just to show you what this looks like. But we'll go over the code for it just a little bit. So the example I'm going to run now is built-in filters. We're going to come to this at the end of the class. My plan of this lecture was to go and motivate some examples and build up, but I think we're going a little too far without something concrete. So let's dig in here. All right, so here's the important part. There's a whole bunch of filters that we're going to talk about. Original, threshold, gray, opaque, invert, posterize, blue, erode, dilate. We're not going to look for the code, but this is our little key for what we can do, for the buttons we can press. So here is our output window. This is the original image. Put the mouse out of the way. I'm going to hit T for threshold. Right, so what this is doing is looking for how different is a pixel from its neighbors. Or no, I guess this is a basic color threshold. Is that true? Yeah, threshold of difference from the neighbors. There we go. So when it goes from the difference between sky and foamy ocean is not great, but the difference between dark ocean and sky foamy ocean is great. The difference between brown rock with brown vegetation, probably ice plant, is different from water and sky. So that's what we're seeing here. Thresholding. Now let's look at gray. So we can grayscale an image with filters. We can, well, the image is already opaque. We can invert it. So invert the color schemes with filters. We can posterize it, tune shade it. We can blur it. We can erode it. And we can dilate. We'll look at sharpen in a moment. Right, so basically all that we're doing is having one little matrix that shows like what for this pixel that we're looking at right now, how do we include its neighbor's information and its own information in to update that pixel value? Right, that's all we're doing. We're just sliding this little box over the entire grid of pixels until we've processed every single one of them. So we're applying a filter to a 2D image, like this. Now, let's see what this looks like. So what we want to do is have an input image, the thing we're taking information from, and an output image. So after we're done processing, where we place the pixels. Because if you do this on the image you're working with, it's going to change it as you go, and it's going to destroy your image. It's going to alter it in ways that are not recoverable. So you want a clean image that you don't modify, that you're taking information from, and you want an output image that you're placing the values into. So here is our sharpness kernel at the top. These little matrices, these filters, we often call them kernels. They're little operations that you can do all over the place. So you'll see these terms used interchangeably, kernels and filters. There you go. Right, so let's say we want to filter. We want to run our kernel, our filter, on this pixel. Right, so we look at the pixels around it. Right, so we apply this on top of it. So we take the value from, we keep a color variable, so we just want to do these operations on all these colors. So we have this color variable, and we're subtracting the color values from all of the -1 pixels, and we're doing a bunch of subtraction, and then we're taking the middle pixel, multiplying it by 9, and then adding that to our resulting color. So we do that and we place it here. Right? And then we move over to the next slide. Ooh, okay, the formatting over. We're sliding it over by 1, not 1.2. And we're coloring the next pixel. And then we slide it over again. Okay, good, that one aligned well. At least one of them worked. To color the third pixel on that row. Right, so this is how we're doing. We're just sliding this filter, this little bit of math, this little math grid that takes information from around a center, from around a pixel, and updates the value of our output image. Right? So actually, I think we'll talk about these later. This is a blur filter. I think we kind of jumped the shark on this by the example that we showed earlier, is the value. So blur can be defined as this. We're just basically the value of the pixel that we want to blur is simply the average of all the pixels around it, including itself. This still adds up to 1. We have 9/1/9 here. It avoids changing the intensity of the image. But you can see how this would just obfuscate the information of a pixel. It just blends it with everything around it. Same with the example. All right. So what would you do if you wanted the image to be more blurred? Any ideas? Any intuition on if you wanted the picture to be more blurred than our 9/1/9 kernel? Yeah. Exactly. We just make that grid bigger. And bigger and bigger. The bigger it is, since it still has to add up to 1, the smaller the fraction is from every pixel it draws from in that larger filter, the larger kernel. including, it has a very small fraction of its own value, of the center of it, right? Increase the filter size. You could also filter the image and then filter it again, and then filter it again, and then filter it again, because each time you make a pixel and put the output image, you use your kernel on a pixel, it averages everything from around it. Well, all those other ones that are around it have been averaged from things around them, and those around them, and those around them. So you're blending the color information. Every time you run the filter, you're like blending the color information across these little kernel spaces, across the little values. Right, so you can apply a filter repeatedly. You can change the filter size. Let's take a quick look at these. So this is convolution example we'll look at first. Oh, pardon me. I closed the wrong window. There we go. Convolution example. All right, get over here. I didn't actually mean to open this. Come on, come on. All right, here we go. Convolution example. This is from the book, so you can look at how they derived it. Basically, we have a few little convolution matrices here, a few filters, a few kernels that we're going to use. We're defining a sharpened one, right? We're using the array notation that we know, and we're simply making an array that looks just like those kernels we looked at. This is our blur filter, 1/9, 1/9, 1/9, 3x3 array. Now, if we go to medium blur, we'll just expand the width and height of that kernel by 1. And so now we have 25 values. And so if we want that up to 1, we have to divide the value for each pixel by the total number of pixels in the filter. And a large one, where we include 49 pixels total. So 48 pixels around our 1 pixel that we care to average, 1 pixel we care to blur. Right? That's what it takes to make a filter. Let's see what it takes to use a filter. So we're going to be using our sunflower image. We're going to be drawing the image to screen. And basically we're going to start at the top left. We're using the constrain command to make sure we keep within some variable bounds. We can take a look at that later. We can look at the documentation for that if you're curious. I'm happy to do it at the end of class if you'd like. And we're setting the filter that we're going to use to be blur medium. So we're going to be using this filter right here. Basically what we're doing, so we're loading the pixels from the window so we can start modifying them. And we're going from the top left, where we're going through the image, each pixel in the image in row. So we're going to do between the X locations being the rows and the Y locations being the columns. And what we're simply doing is we're using our convolution function, which we'll look at in a moment, at that pixel XY, using this filter with a particular matrix size and the image, so our coast image, the thing we're using, and we're getting the color for that location using that filter back. And then what we're doing is we are looking at the XY, we're getting back the array location from those XY values, and we're putting it into our pixels variable. That convolution, that blur we just calculated, is now being put into our background image. Then we're updating the pixel, setting no stroke, no fill, and we're drawing a rectangle. You'll see why in a moment. So this assumes our X star directs into the same as the image. This is actually a box filter. We're going to be sliding a box around the screen and filtering just inside the box, which is why this isn't like window height and window width. This is the width and height of the box that we're looking at. Convolution, right? So we want to see what our color values. So if we're adding up a bunch of color values, if we're like averaging across the grid or looking at our kernel and taking various weights, we want to get the color channel information for each one of these. So the red, what our final red value green value and blue values should be. And we're offsetting, so we want to make sure our matrix numbers are correct. So our matrix is basically the size of the convolution that we're going to use, the size of the kernel. And so for the size of the kernel, we're simply going through it just like we'd go through any other grid. And we're looking at the X and Y locations of the particular surrounding pixel in the kernel we want to look at. So in this case, if it's the 19 by 19, the blurring that we looked at before, this first, the 0, 0, will just be that top left corner. So what we want to do is take that top left corner pixel color from our image, and we want to see what weight that has. So in our matrix, since we are using blur medium, we're going to be looking at the very top left of that filter, and we're going to multiply the red value there by the value in the matrix, so 1/25. So the red color in that top left divided by 25, and then we're adding that to our red total. We're doing the same for green and blue. And so we're basically going through that entire filter and adding up the RGB totals by 1/25 with each pixel in the image. Does that make sense? All right. And so we want to make sure, so what this constraint function simply takes, you give it a number, and it makes sure if that number is between 0 and 255, or between the two variables you give it. Because we're using colors, we want it to be between 0 and 255. So if it goes over 255, it will be 255. If it goes under 0, it will be 0. Otherwise, it'll leave the value alone. And we return the color that our convolution made for us. And get that color, and we plunk it in the image. All right, that's all the code. This is a little complicated. I encourage you to take another look at this to really understand what's going on. This is sort of like the heart of making your own filter. It does some really interesting stuff for being a relatively small amount of code. All right. This is our medium blur. Right, can you see how the pixels in the blur area are different than the pixels around it? Well, we're just applying our filter. We're just we're blending a bunch of pixel information together and plopping it in the middle. Right, so you can see on the leaf, I guess we use that bottom leaf down here just below the cursor. You can see how that yellow now extends much lower than it would otherwise. We are doing like just blend between colors. We're getting a lot of intermediate colors. The edges are hard to see. It's the opposite of sharpening. Let's take a look. Let's change our filter. So we had defined 4 filters: sharpen, blur, small, blur medium, blur large. Let's do blur small. Whoops, whoops, whoops. Get out of here. And run again. Oops, there we go. So now you can see the blur is less distinct this time, but it's still blurring, right? The blurry background becomes just a little less distinct. Let's change this to blur large. Blur large. There we go. Right, now this is a lot fuzzier, right? Because now we're blending 48 pixels into one instead of 25 or 9. Let's check out sharpen. Sharpen. Right? Now, basically, every pixel is having less information. Is removing the color bias from all the areas around it. And so you can see it like really heightens, like it even like makes up, levels of detail here. things look very, hyper focused. Things are very up close. All the edges are very prominent, and all the changes in colors are very harsh. Right, so this is a pretty aggressive sharpening algorithm. Is that what you thought it would look like? So if you use like Sharpen in Photoshop, they have a much, if they don't use this basic Sharpen algorithm, they have things that are much more nuanced. You can configure that Sharpen kernel through a lot of different ways. You can change like the radius of it. You can change how much subtraction there is from the colors around it. You can play with it a lot. But through that UI where you play with all those things, basically all you're doing is making a new one of those kernel matrices, just kernel grids, and just using it. It's the same operation. And so you can do this on the whole image as well. So we'll look at that example. Doing these things in proper order. So this is convolution whole image. Oh gosh. Luckily it saved itself. All right. So our controls are the original image, 4 different levels of blurring, and sharpen. Those are the numbers you can press. So here are our filters: sharpen, blur small, blur medium, blur large, blur huge, 400 pixels averaging. And so instead of doing it around a window, we are basically doing it for the entire image width and height, calling our convolution with our filter. Okay, there's our image. Blur level 1. Original 1. Original. It's kind of hard to tell. The video recording may be a little handier here. Does blur small, blur medium. Okay, that's definitely more visible. So I toggle between medium and original. Small, medium, original. Here's our blur large from before, our 48 pixel blur. Right, it's getting pretty fuzzy. Large, medium, small, original. A or B. This is like a vision test, right? Can you read the letters now? All right, and so this is our huge blur. Ooh, it took a while to process. Okay, so because we're doing a lot more math, it took a long time for it to go. So let me take it back to original. And then I'm going to press 4 for huge blur. Now, so it took appreciable time. There was number crunching that happened, right? There was a visible amount of time taken, and it was simply doing a bunch of additions and subtractions and multiplications, right, to make this blur. 3 took a little while. So 1, instantaneous. 2, for human perception, instantaneous. 3, took a moment. 4, 2-ish seconds. Original, fast. Sharpen. Right? This is a very aggressive sharpening algorithm, but now you can see every little speck of inferred dirt or inferred sand in the foam. Right? Questions on this? Here, everybody's checking their eyes now. All right. Edge detection. So we can also use filters. Oh, I'm sorry, I didn't flip. Thank you for letting me know. I'm managing a lot of windows today. Edge detection, right? So now we can start looking, now that we have this idea of looking at a pixel and then comparing it to its neighbors, doing a little math on it where the neighbors' values are involved, we can now start doing things like looking at edges, right? So they're often marked by large differences in the value of adjacent pixels, right? So what you want to do in a copy image is store the distance between adjacent values so you can compare them. And then you want to look at large differences, which often indicate an edge. So here's a little formula for us. So for every pixel, we want to, convert that location of the pixel to the one-dimensional array that we are dealing with our pixel array in our images in our background, right? And so we're getting the location of one of the right picture, or of one pixel location in an image. And now we are getting the pixel location to the left, right? So x minus 1 in this case instead of x. X moving over by 1, getting its location, its collocation. Now, the new color is the difference between the left and right pixels. So what we're doing is we are getting the brightness value, which we're looking at the luminosity values here, between the pixel we care about and the one to its left, and we're getting the absolute value of their difference. So one can be greater than the other. We want to make sure that we're looking at the distance and getting rid of any negative or positive values. We just want the raw distance. And now we're getting a color from that luminosity value of the difference, and we're stashing that in the pixel. So the more different they are, the brighter it will be. The more similar they are, the darker it will be. Right? Where will this code fail? Look at it again. Where will it fail? We're moving from left to right. Is that all that we need to do? Yeah.
Also needs to be raised left,
Close. You're so close.
up and down.
Up and down. There we go. We're doing left and right and not up and down. It won't detect horizontal edges, just vertical ones. Let's take a look at the edge detection. Another example from Schiffman. All right, so this is doing exactly what we said it would. So we're looking at the sunflower image, and we want to toggle between showing the original image and a set of pixels that look at the edges of that image, that show the edges. So this is exactly what we're doing. We're going through the entire image in a nested for loop. We're getting the pixel location we care about. We're getting the one to its left. And we're getting the difference between them, between its neighbors. There we go. Original image. Press O to turn it off and on. So what do we see in here? This has the same flaw, right? This is the exact code we ran. We are seeing edges that are more horizontal than vertical, right? So notice that we're seeing, like for this leaf right here, we're seeing the one that when it goes more straight up and down, we see white more strongly, but when it's more left to right, we don't. So since we are seeing like this one very strongly, but we're not seeing any for this really stark edge in the brick above, right? This is a very clear color difference. This should be an edge, but we don't even see it. It's not detected because we're only looking left and right, not up and down, right? So when you're looking at a pixel, you want to see if it's an edge. You want to look up, down, left, right. There's a bunch of operators. The Laplace edge detection operator is the most entry level and the one that does a good job and is fairly simple. So we can maybe talk for that during office hours if you're interested. Laplace edge detecting operator will do a pretty good job of on this image. So it's sort of like a challenge to you if you want to try to update this to do horizontal and vertical edges. That'd be pretty cool. There's a whole bunch of built-in filters. See, we just sort of looked at those. Threshold, gray, invert, posterize, blur, opaque, erode, dilate. All of these are just grids that we apply. Some of them have some additional values like level. So if you want to blur, it has all of our levels. So every time you increase the level, it increases the width and height of that kernel of the filter of the matrix by 1. And if you go more than like 4, it's going to take a long time. So the level 4, the huge filter that we had, took about 2 seconds on a fairly small image. You go to 5, it will take another power of 2 again, more. Do the math on that. So going back to the built-in filters, just take one quick look at them again. And we can see how we use them here. So our current filter, these are defined for us in processing. These are available for you just to use. You don't have to define the actual kernels themselves. You don't have to do the math. Filtering is already built in to processing. And so there's a filter command that's given to you. Basically, posterize and blur need a second parameter, a level of value. All the other filters, they run in a basic form. And so you use the filter command, and depending on which filter you give it the filter, and a secondary parameter, or just a filter. You can see setting all the filters here. And what the filters do is they, by default, filter the current window. Yes?
Does the filter command only then work for the pre-defined filters that come with processing, or if you define your own filter, could you then use the filter command?
You can define your own filters, but I haven't actually done this yet. So let's take a quick look at the documentation and find out. There's the filter reference. Let me switch to browser. There. So here's our filter reference. Here are all of our pre-given filters, pre-rendered filters. You can see what they do. So we have a kind. Okay, so no, it does take one of the defined filters. So you'd have to make your own filter. You'd have to do it, roll it yourself to make a different one. But normally what you do these days are, apply fragment shaders, which is another topic that we probably won't talk about in this class, applying shaders. And that's where most of this is done now. It's a much more convenient representation for modifying your output image values in 2D and 3D. I'm happy to talk about shaders in office hours. I love playing with shaders. Shader Lab and Shader Toy are very fun. Good question. Any other questions? And the last thing I wanted to cover here, since I didn't see any hands, for the slide deck before we talk a little bit more about other class materials, is anti-aliasing. So you may have seen jagged lines in video games or imaging. This happens when your pixel values, when you're drawing something, there is no, like you're saying, well, this filter is part of a line or not. Well, the math can be pretty stark as you rasterize or turn something that's a logical line, as in a mathematical line, into a pixel representation, quantize it into little boxes, which Arpreet will be talking about next week. This anti-aliasing is a little kernel that smooths out those edges. It's basically a little localized blur to make the lines look less jaggy, to fill them in a little bit with intermediate values. And that's why we use the smooth command. So you've seen us use the smooth command a few times. That's to make our lines and shapes look better, to make them look less jagged, less stark from on pixel to off pixel, and smooth that out a bit. All right, we got through filters. Any questions? Did the information filter in? Maybe bad jokes don't work either. All right, so I imagine for most of you, this will take some review. But the goal of this for media computation, for the purposes of cinema and digital media's curriculum, is to expose you to the layers of technical depth, the machinery, the mechanism behind the tools you use. And so this is one very pertinent example for those of you that deal with visual images, video, games. Filter works for all of them. It's a very prominent technique being used. And now you know how it works. And you can, maybe with a little bit of elbow grease and reviewing the slides in the lecture, make your own. Okay. Let me go back to the browser. Let's talk about assignment 6. Because you may notice, and this has been up on Canvas for a while now, your project proposals are due on the 15th. We could potentially push this back a little bit, but how many of you have started forming your teams? Yeah, okay. There's a small number of team formation here. So this is what you're going to want to do. You're going to want to chat with your fellows. You can even use the Discord channel to see, hey, I'm interested in this sort of experience, this sort of art, this thing. Maybe make a small game. Maybe make a little art project, visual art project. And see if anyone's interested. So we're looking at teams of 4 to 5. All right, so assignment 6. You can read the descriptions here. You want to make a brief interactive art piece or a simple game. Groups of 4 and 5. You must write the program that generates captivating visual output, and there must be some form of user interaction. Those are our 2 primary requirements. Right, so you go to a little more detail, like it should be between 30 seconds and 2 minutes, depending on complexity. You should use a lot of the ideas from class. The scale, the size and complexity of the project should be something that's worth 15% of your total class grade. So I'm expecting some significant code and complexity here. You're allowed to use libraries. You just need to document when you use code that's not your own. So if you use external libraries and they're complex, that doesn't count towards your complexity that I wanted you to deal with. So make sure the complexity of the code you write is appropriate. All right, if there's a file in your code that's not yours, make sure you comment about it at the top of the file. Basically, if you're using something that's not yours, reference it. Let me know where it came from. This is so I don't have to do any SJC request or anything, right? I want you to just be honest with what you've used elsewhere, and we're very happy for you to use things from outside of class and integrate into your project. That's how art works. So if you have an existing piece of code, if you've modified an existing piece of code, make sure you comment that as well. Like if you use Stack Overflow or something, say, hey, I got this code from Stack Overflow. All right, so failure to follow these guidelines can amount to plagiarism, academic dishonesty. Just don't do it, please. Learn and be happy. So kind of more interested in seeing nice, simple, original ideas than something that's complex and using a lot of other people's code, right? We want to show off the pedagogical goal here is to assess what you've learned and how you can bring these ideas together to make something interesting. The more you use outside things, the harder it is for us to assess, right? Okay, so plan submission. So on Canvas, And I've ran into a little snag on this. It looks like the university may have disabled your ability to see the people section in Canvas, which is very annoying because that is the critical tool to allow you to form your own groups. So right now I'm working on exactly the technical mechanism for you to form your own groups. It may be a Google Doc or a Google spreadsheet at this point where you put your names and emails that you associate with your group. We'll get back to you on that. So we want you to form a group, and which is submit a proposal in the form of a brief plan. Only one person in the group needs to submit the proposal. And it's basically we want you to include a 1 or 2 paragraph description of what you want to make. And then we want you to indicate whether you want to go on the last day of class or the second to last day of class. And note, we're going to give a little grade bonus to those who go on the second to last day of class to compensate you for the less time you have to work on the project. Okay. I think that's about all I need to say about that right now. Any questions? All right. Let's go over the assignments. So, labs aside, everything that's due in the class is now listed on Canvas, right? And I did yesterday morning give you access to assignment 5, even though it's not due until November 22nd. Since I'm out of town, I wanted to just be able to see it early. Our next lab, we'll go over assignment 5. And we'll have a lab next week. And then we have the final and the midterm. Midterms are coming along and grading. We parceled them out to the TAs. So I'm assuming we'll have the grades done probably sometime close to the end of next week. Is that realistic? We'll be in communication with you in any case. All right. 1 minute left. Last words? Yeah. All right. I will see you all after Thanksgiving break. Have a lovely time. Enjoy yourselves, your families. Good luck with your next 2 weeks. And I will see you back soon.